So we have here a compound lens problem, which means you have two lenses. A 1.2 centimeter object is kept 50 centimeters from a converging lens of 40 centimeter focal length. 300 centimeters from this lens is a diverging lens of 60 centimeter focal length. Determine the reality, which means if the object is real or virtual, orientation, magnification of the final image, and draw a ray diagram to scale. It's a typical compound lens problem that you have in this course. To solve it, you have to apply the lens equation twice, the thin lens equation twice. So let's apply it first to the first lens. The focal length of the first lens, which I'll call f1, is plus 40 centimeters, plus because it is a converging lens, and the focal length of the second lens is negative 60 centimeters, negative because it's a diverging lens. The distance between the two lenses, which I'll call d12, is 300 centimeters. So it's good to write all these up front. The height of the object, which I'll call h1, is 1.2 centimeters, and the distance of the object from the first lens, which I'll call s1, is 50 centimeters. These are all the givens. What we have to find out is the final image. The distance is located from the, say, the initial location of the object, whether it's real or imaginary. A real object is a real image is one that can be caught on a screen. A virtual object is one that can be seen but not caught on a screen. So it's very important to remember that distinction. But in terms of the lens equation, all these are given by the various sign conventions that we have for these lenses. So let's proceed to find out the location of the image from the first lens. So the thin lens equation, which I've abbreviated as TLE in the notes, is 1 over S1 plus 1 over S1 prime equals 1 over F1, where S1 is the object distance, S1 prime is the image distance, and F1 is the focal length. The object distance and the image distance are measured from the plane of the lens. This tells me that 1 over S1 prime is equal to 1 over F1 minus 1 over S1. Substitute the values. I get 1 over 40 minus 1 over 50. I'm not careful to put units. So that turns out to be 50 minus 40 divided by 50 times 40, which is 1 over 200, which means that S1 prime is equal to 200 centimeters. Now I'll put the units. The distance of the first image from the second lens is going to be the new object distance for the second lens. That new object distance will be called S2. So S2 is going to be D12, the distance between the lenses, minus the location of the first image. And so that's going to be 200 minus 100, sorry, 300 minus 200 centimeters, or 100 centimeters. Now the image of the first formed by the first lens will function as the object for the second lens, and that object distance is 100 centimeters. Now while we are at it, let's also calculate the magnification. The magnification from the first lens is given by the magnification formula, and that formula is negative S1 prime over S1, which means it's a negative image distance over the object distance, and the magnification is also equal to the height of the image over the height of the object. And so I can certainly get the, I don't know the height of the image, but I certainly know the image distance and the object distance thanks to the TLE. So I can find that out. So negative S1 prime is negative 200 over S1, which is 50. And so I get H1 prime over H1 equals negative 4, which means it's magnified 4 times and inverted. So let's also find out what H prime is. H1 prime is, it's going to be negative 4 times H1, and so that's going to be -4 times 1.2 centimeters, because the original object's height was 1.2 centimeters, and this gives me -4.8 centimeters. Good to keep that in mind. As we draw the ray diagram, we have to get these results. Now the TLE, or the thin lens equation, can be applied once more. So the second application of TLE tells me that 1 over S2 plus 1 over S2 prime is equal to 1 over F2, and so I get from that 1 over S2 prime is equal to 1 over F2 minus 1 over S2. So that's going to be -1/60th minus 100th. So that will be -160 over 60 times 100. I dislike using calculators for these things, but you feel free to use calculators. It's easier to just do it by hand. So 4 divides 15 times into 60, so that gives me -4 over 150, which means that S2 prime is -150 over 4. Now I'll put the units, which means S2 prime is -37.4 centimeters. So all the results are coming in thick and fast. The minus sign actually means that the image is formed to the left of the second lens. So that's something we have to watch out for when we draw the ray diagram. So image formed to the left. Okay, so the image is actually on the entry side of the rays, which means the image is going to be virtual. So we can straight away say that the image is virtual. Lastly, we have to find the magnification again for the second time, and so I'm going to do that next. M2. By the way, the height of the object for the second lens is precisely the image height of the image for the first lens, so that's going to be -4.8 centimeters. And also M2 is going to be -S2 prime over S2, so that gives me -37.5 divided by 100, so that's 0.375. So but M2 is also equal to H2 prime over H2, which tells me that H2 prime is equal to M2 times H2. So H2 was 4.8 and -4.8, and M2 is 0.375. So when I multiply the two, I'm going to get -1.8. This part I worked out in a calculator beforehand. So first of all, 1.8 is bigger than 1.2. So the image is going to be magnified and inverted, but just by a bit. And this is a signal that it's virtual because it's on the exit side of the ray, not of the lens, not on the entry. It's on the entry side of the lens, not on the exit side of the lens. So we have all the things we need. Now we have to just confirm everything using a ray diagram. Now it turns out that this mathematics is much easier than drawing the ray diagram. The ray diagram is quite a huge pain, but it's wonderful to see everything come out nicely. So I have to choose the scale. Now looking at my numbers, I think a good scale to come up with would be something of the order of along the y-axis, I'm going to keep things as is. Because remember, I'm going to get something like 4.8 centimeters, which is about this big. So I have to keep my y-axis as it is, then things will look good. X-axis I have to take down quite a bit, because first of all, 300 centimeters is 2 times the width of this paper, so I have to bring it down quite a bit. I'm going to choose 15:1 for the x-axis. So if I did that, the distance between the two lenses, which is going to be what, 300 is going to become 300 divided by 15 or 20. So what I'll do is I'll first draw my, I know that I should at least keep 5 centimeters for the image. So I'll draw my optic axis somewhere over here, hoping that nothing will blow up and I won't have to redo this video, which would be a pity because it's already 10 minutes long at this point. But let's see how it goes. So that's my optic axis. I'm going to make it a little bit longer. And I'm going to keep my object at the very end so you can barely see it on the video. So that's going to be my object. And the height of the object is going to be 1:1, which means I have to make it exactly 1.2 centimeters in size. The ray diagrams are going to only be as good as your drawing skills. So don't feel bad. If you did the math right, you'll be fine. Now it's kept 50 centimeters away. Now 50 centimeters in the language of 50 centimeters divided by 15. 50 divided by 15 is going to be 10 divided by 3 or 3.3. So I'm going to keep the first lens at 3.3. It's actually 3.33, so you can already see the problems in drawing this accurately. When you're drawing a lens, don't make a production of it, just draw a vertical line like that. The second lens is located a distance 300 centimeters from the first lens. I've already said that 300 divides 15 20 times, so I have to keep it here at the 20 mark. So that's my second lens. Try to make it as perpendicular as possible. It's not very important, but it's good form. Now, because these are thin lenses, it's sufficient to draw a single straight line. Now, for the most important part, and that is the drawing of the various rays. Now, unfortunately, here I have fountain pens which don't exactly make a thin line, so I have to urge you to use a proper tool like a ruler or something when you do it. The first ray goes parallel to the optic axis and then converges through the focal length. Now the focal lengths I've forgotten to put. 40 centimeter focal length divided by 15 is going to be 40 divided by 15 is 8 divided by 3, and 8 divided by 3 is 2.7. So I'm going to put a 2.67 actually, but I'll put a 2.7 over here and a 2.7 over there. I'll tell you why I'm putting a 2.7 in two places, because there are 3 rays you can draw in this procedure. So the first ray you draw passes through the optic axis. The second ray you draw will go straight through the middle of the lens, undeflected, because that's what you have for a thin lens. Oh, so I should have made the first one slightly bigger, because it's going to intersect a little bit beyond, I think. How about that? And then the second one goes straight through the optic axis. The two straight lines intersect at a unique point, which are not parallel, so that you can stop the procedure there. But you can already see how sensitive this is to small movements. If I move this even slightly, this goes up quite a bit. So it might be useful to have a third ray to make sure that you have the proper ray diagram. And that's the reason for the third ray, which I sometimes like to call the verification ray. And just to make things nice, I'll so the third ray actually is the one that goes to the focal length before the lens. So to even be able to draw this, I have to go down a little bit on this page and see if I can swing it like that. Yes. So you see that if it goes through the first one, then I'll draw the verification ray with a dotted line. So it goes through the first focus, hits the plane of the lens, and then from there onwards it goes parallel to the optic axis, because that's what all lenses are supposed to do. Now you see that there's a triple intersection looming, and that triple intersection should be trusted more than the double intersection point. So I'll take the this point to be the one, because here you can see how sensitive it was to the intersection over there. The angles were so small there. So hopefully this will turn out to be 4.8. Whoops, it's 5.2. Actually 4.8 is where the double intersection point is. So I'm beginning to question my drawing skills here. So if I have to cheat a little bit and take 4.8 over there, so let me compromise. I know the image has to be 4.8. So I'll take it somewhere in between the triple intersection point and the double intersection point, just to make the rest of the diagram come out decent. Okay, now the second diagram, you've got to play the same game. The focal length of this lens is 60 centimeters. Fortunately, 60 divides 4 by 4, 15 nicely. The answer is 4. So I can just go 4 on the left and 4 on the right. Now, mind you though, that's a diverging lens. So the only thing that you can be absolutely positive about is that it goes through the focus, through the center of the lens, undeflected. Okay, that's good. Now what a diverging lens does is the first ray that it sends out from the object appears to converge into the focal length here. So into the focus before the lens. So what I'm going to do is I'm going to send this ray out, and then the story of this ray, I forgot to put arrows. I should put arrows everywhere. 2 and 3 for the third ray. So we are still in the first ray on this one. It's going to diverge. That's what a diverging lens does. But how is it going to diverge? It's going to seem to diverge from the focal length there. That's your path 1. And the seeming to diverge means that. So we already have a double intersection point. That's the image. We can take it and run. Or we can also be somewhat honest and try the third intersection point. And there what you do is you you know what, I'm not going to do the third verification ray. I'll just stick with my 2 rays. I think the diagram is already quite cluttered at this point. Yeah, so this is good. Let's try to find out the height here. I get 2. It's supposed to be 1.8. I get 2. So it's not a bad diagram, and you can measure the other distances and see how it works out. So don't take this to be gospel. The gospel is contained in the proper mathematics. This is taken to be an indication of how things are in the ray diagram.